I'm going to look at the first Mandelbrot exercise here. And so I just want to solve this parallelize this with just a plain old parallel region without using any work sharing to begin with. Okay, so here's the main loop nest, and so let me start with adding a parallel region. And use default none, and I'll come back and think about the shared and private variables later. So meantime, let's just add in the parallel region. Okay, so what I want to do is essentially instead of running the outer loop from all the way from 0 up to endpoints, what I'm going to do is calculate lower and upper bounds for this loop for each thread. And so I'm going to replace the bounds here with low and high. And then in order to calculate those, I need to first of all to get my thread ID. And then to also get the number of threads. Okay, so now I can calculate the number of iterations per thread. So the number of iterations is endpoints. So I can figure out how many iterations I want each thread to execute. So iterations per thread is going to be okay, and I actually want to round up here. So integer division in C rounds down, which isn't what I want. So I'm going to use a little trick here. So if I add threads -1 to endpoints and then do the division, that should give me the rounded up. It should give me the division and round up. So then I can go ahead, and so the lower bound is then going to be my thread ID multiplied by the number of iterations per thread, and the upper bound is going to be the lower bound plus the number of iterations per thread. Then I have to worry about if things don't divide nicely. So strictly speaking, I need to fix the upper bound up. So if the upper bound is more than endpoints, and I need to set it equal to endpoints. Otherwise, I might run off the end. Okay, so that's hopefully done the correct calculation to produce a lower and upper bound for every thread. And so now the remaining thing I need to worry about is the data attribute scoping. Yeah. Okay. So actually, what we'll do here is basically let's see what the compiler does in terms of error messages here. So I've specified default none, but I haven't said anything where anything is private or shared or reduction yet. So let's see what the compiler will do about that. Okay. And So actually gets, yeah, something very sensible. Okay, so it tells me that the variable num outside and the variable z and the variable c must have explicitly specified data sharing attributes. Okay, and it even tells me where it wants them. So that's a for once it's a fairly fairly understandable error message. Okay, so Z and C and num outside are the things I need to care about. So think about Z and C first. Well, clearly, if what I want is a separate copy of C and Z for every thread, because basically C is calculated from the values of I and J. Different threads are going to have different values of I, so I clearly want different values of Z, and then Z just starts out as being C and is then the thing that's iterated. So those are things that I want a separate copy for every thread. Having them uninitialized copies is fine because I'm going to give them values there before I use them. So that's no problem. Final thing I have to care about is num outside, and so this is the thing that's forming the sum that counts the number of points that are outside the set. And so that is a classic reduction pattern. So that's precisely how I can handle that. Declare num outside as a reduction variable with the addition operator. Then I will get private copies initialized to 0. Every thread will do an accumulation, a partial accumulation of the result in its private copy, and those will get added together at the end of the parallel region to produce the result that I want. Okay, so hopefully that should do the job. Brave and try with a few threads. Okay, that looks like the right result. So happy with that. Let's just check that. So it's on one thread. Yeah, good. So I would say timing results on the login nodes are not particularly reliable, but I'm getting a speed up of, well, 2 and a bit on 4 threads, which is better than nothing, but not fantastic. Let's try a few more threads. Okay, so a bit more speed up, but certainly not linear. Okay, so I think already discussed in the chat earlier on today, the reason we don't get perfect speed up or good speed up for this problem like this is because the problem is not well load balanced. So what happens to this inner loop down here is, which has this break statement inside it. What happens in practice is that if the point is inside the set, then it goes the full max iter number of iterations in this loop, which is 2000. But if it's outside the set, then this test gets triggered pretty soon. So typically in less than 10 iterations. So there's a lot less load on the points that are outside the set than the points that are inside. And because of the geometry of the set and the way that we've chopped it up, so different I iterations will have very different amounts of work to do, depending on the value of I. So this is not a particularly well load balanced problem. If we do this equal division of work across threads, then we get some improvement in performance, but not as good as what we could achieve. Okay, and so actually there is there's a neat little trick we could do there here to fix it. So instead of giving a block distribution of iterations to threads, we can quite easily do a cyclic one instead. So if I change this line here, I'll just comment out that version. So instead of going from low to high, so if I start at I equals my ID and go up to number of points, and instead of incrementing by 1, I increment by the number of threads. Yeah, okay. So I'm basically that gives me a cyclic distribution of the iterations, and because the way the load is distributed here, it's actually sort of neighboring values of I actually have reasonably similar. Neighboring values of I are neighboring slices through the Mandelbrot set, so they actually have fairly similar load. So in this case, doing a cyclic distribution does a good job. So hopefully, I rebuild that and run it on 8 threads again, I should see something better. Yes, okay. So I've got roughly halved the execution time from what I had before on 8 threads, and now I'm getting somewhere reasonably close to an eighth of the 1 thread execution time. As I said, without measurements on the login nodes are not particularly precise, but I hope that's, without running a batch job, I hope that's reasonably convincing. Okay, does anybody have any questions about that? Okay, well, good. So I hope you managed to come up with a solution that looked roughly like that. Okay, so for the next one, I'll tell you what I'll do. I'll swap to Fortran. See if I can. I'll see if I can cope with messing with my brain by swapping languages. So Fortran version. And so clearly you would not normally use just a bare parallel region to parallelize straightforward loops like this. I think it's useful to do it as to make sure that you. I find it helpful to get people to really understand what's going on. That yes, you really have the parallel region really just does create threads, and they all do execute the same code by default. Otherwise, just introducing you to straight to OMP parallel do just looks like, oh well, here's some magic that makes your loop go faster, and you don't really get a good appreciation of what's really happening. Okay, so but the natural and much nicer way of doing it would be to use a parallel, in this case, parallel do directive. Okay, and I have to remember which variables we need to care about here. It's slightly different. So again, I need private copies of C and Z, but also of iter here as well, the iterator for the iterator that I'm going to use for the while loop. And then also still need reduction. I'm outside. Let me just check that works and see if I've got that right. To start with. Okay, and read threads, what happens? Okay. Oops, that doesn't look right. What did I do wrong? Looks okay to me. Oh, I know. This is Cray. This is a. I remember. This is actually a Cray Fortran compiler bug. Okay, it produces like it doesn't actually compile this correctly. Yeah, I remember. I have seen this before. So what can we do here? Does anybody else see that? That any other Fortran programmers see that you don't that they observe that it gives very slightly the wrong answer on multiple threads. Yeah. Okay. So I think so. Let's swap to a different compiler and check. I need to fix my make file as well in that case. Okay, that looks better. Yeah, so this is that's unpleasant. That is it's a bug in the compiler optimization in the Cray compiler that causes that to happen, which is really not very nice. But a good illustration that compilers are not infallible. Okay. Right, what else? Okay, yes, so again, I have a load balance problem here, but now because I'm using parallel do, I can solve it with a schedule clause. And in fact, pretty much anything other than static with a reasonably small chunk size will do the job here. So, dynamic 1, for example, should be fine. Yeah. Okay. So again, you see roughly double the performance or half the execution time if you use a schedule that's going to balance the load reasonably versus one that doesn't. Okay. Does anybody have any questions? Oh, what's in the chat here? Okay. No, it's Charles saying she's got it. Yeah, she's got the same. Say she saw the same bug. Yeah, go ahead.
With which command can I show the threads from the environment variable?
So you want what? So you want to print the number of threads from inside the code?
Yes, or in the CLI. In the CLI.
So there's a couple of ways you can do that. You can create a parallel region and then call OMP get num threads from inside. Clearly, okay, but doesn't work from the master thread. So you can call OMP get max threads. So same function I talked about that returns the value, the number of threads that are going to be used for the next parallel region. Okay, so that will be what you set in the environment variable, provided you didn't change anything in the code. Okay. If you absolutely want to know what the environment variable says, then you would need to read the environment variable directly with getenv. But normally you wouldn't do that, because what the environment variable sets an initial value for the number of threads for every parallel region. So that sets the initial value of this internal control variable. But then your program can then modify that by calling, for example, by calling OMP set num threads inside the code. So what OMP get max threads returns is the current value of that internal control variable for that thread, because that that value can vary between different threads if we're talking about nested parallelism. Does that make sense?
Yes, sure. Thank you.
Yeah. So, yeah. So it's OMP get max threads. It was in the last lecture that, yeah, that's the function you want, that will tell you how many threads, or at least an upper bound on the number of threads that are going to be used for parallel regions. And so in normal circumstances, that will be equal to the value that you set in the environment variable. Those names are a bit confusing, and they were designed. They were in OpenMP from the very beginning, but the notion of internal control variables wasn't. So we ended up in a situation where the functions called get and set for num threads don't do what you expect, or at least they're not they are the so get num threads does not return the value of that, is not get the value of that internal control variable. It gets, if you like, it returns the number of threads currently executing. So if you're expecting get and set to be getters and setters of something, then it's of the same thing, then it isn't, which is slightly unfortunate. Anything else? Okay, so again, if you will be around until 5 o'clock, another 40 minutes or so. If you want to ask any more questions, if you want to carry on working on the practical exercises, but once again, I recognise it's getting late in the day. You may well have had enough for today, and you prefer to head off now. That's absolutely fine. So if you but you can, obviously your accounts are still available. You can work on stuff between now and next Tuesday if you wish to, of course. Anything else to say administratively wise? Okay, yes. So I'll send a reminder about this, but the session next Tuesday will start at 9:30 rather than 9 o'clock. All our sessions will be have been recorded, so we will post the videos on the course web page. So Andrew says, do you use the same priority codes? Unfortunately, no. So outside of the actual class time, the reservations won't work. You can use the short queue though. So you can say, so in your batch script, if you instead of minus QoS equals standard, you can do minus QoS equals short. Okay. And that should give you better turnaround than the main queues. But the reservations are only for the days of the actual days of where we actually have live sessions. Okay. Anything else? Yeah, so videos will get uploaded probably if not very soon, then certainly later this week. The videos of these sessions will be up on the course page. And again, just remind you of the opportunity that if you're working on a code on your own code, if you want me to take a look at that, or try and offer you some advice on how to handle it, or whether you've got some performance problems or anything like that with OpenMP, then welcome to do that as part of next Tuesday's session. Okay, so yeah, so we'll be around until 5 o'clock if you've got any more questions. Okay, last call for any questions before we wrap up for today. Okay, great. Thanks very much, and I'll hopefully speak to you next week.